The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Yeah, so you have basically two semiconductors to start with, one N and one P-type N, P-type. So, for example, you have on the left-hand side, you have a P-type, on the right-hand side, you have an N-type. And there will, since you have a high concentration of electrons on this side, the electrons will basically jump to this side, and you have a high concentration of holes in the P-type, and the holes will basically jump to the other side. So you will end up with this space charge region that Gang talked about last week. And this is basically the characteristic for these bigger junctions. I just draw one layer where they see expanded a little bit. So you basically have a neutral region here, which is kind of important to know too. So you have your P-N junction, and then you have your contacts here, which connects. And basically, in case you impose the solar radiation or something to this junction, you can generate a voltage out of this. Or if you close the circuit, you can generate basically power. For now, I just talked about the open circuit voltage. So this is the first thing that basically happens when you join these P-N junctions. This space charge region builds up. Or also the region layer off. And over this you basically also you can generate a certain built-in voltage out of the for example. So so you have the space charge region, which is right here, and then you can basically draw, for example, the carrier concentration. And so for the electron, so this is type, N-type. The electron basically increases in concentration and then each steady state. So you can basically say you have a neutral region here. You have a E field generated here. And the other neutral region here. So in case you have, for example, a photon comes in, we'll talk about this later, but when a photon comes in, it generates an electron program or an exciton, so they're still very close to each other. These excitons, basically, when it's generated, they have to be fused in this neutral region to this space charge region, but they basically get separate. So for this case, for example, when you have coming. The E field is in this direction. So basically the electron will basically drag through this. So the electron will force in this direction. So the electron will basically tunnel through like basically gets separate from the hole and jumps on the other side. And you end up with just a positive charge here. And due to the neutral region here, basically have diffusion of your electron and the holes to the contacts in here. So further, so this is the carrier concentration, and then you can draw the charge in there. So negative charge here, positive charge here, and the E field looks like so the E field that is generated inside this space charge groups like this, or more accurately, it's probably more like sharp. And I think this was also when we talked about the dielectrics last week. He said something that this is kind of important, and this later intelligent people from not that intelligent people. Talk about the dielectrics. The dielectrics is just the spatial expansion of this condition relation. So as I say, when this E here drops to 1 over E, this is basically this kind of, so just say up to a certain point the E here basically drops down to a certain value. You can just say this is basically a spatial extension, but up to this point, an exciton, when it comes, it will start feeding this space charge region, and it will start to separate into an electron and one will there. And then I wanted to talk about so in the real case, then when we actually have a photon coming up to the N junction. Maybe I start with the band diagram. So when we join the two semiconductors, we talked about in the last lecture, we have to do band alignment, since the thermionics have to be the same. So this somehow. So this will be the fan level, or so that's the conduction band, and balance band, and let's see what happens is the photon comes in, and an electron is basically excited with the conduction band. And at the same time, it gets separate. So first we have this state, the excellent state, and then when it comes close to the space charge, it gets separate, and it ends up in the conduction band of the N-type system. And this basically changes the family level. So what we end up with is the family level actually increases, and so you increase the number of atoms, the family level will increase, and when you remove an atom here, you end up with an hole here, so you basically decrease the family level here. So you end up with some kind of region which is this is basically the open circuit voltage that we see. So the difference between these two terminals is due to the exchange of electrons and holes. This is basically the open circuit voltage of itself. And in the ideal case, obviously, you could basically go all the way, so it means the maximum open circuit voltage that you should get should be this.
So the electron goes to the conduction band of the material, right? Is it because that's easy?
Yeah, I mean, what was the question?
But could electron also go to the conduction band of the material as well? Yeah.
That's a good question. I was thinking about that too, whether it's actually a step like this that goes and then basically goes down.
Yeah.
Very good question. I think I can provide an answer. We move on.
You want to answer?
Right. Yeah, well, it's a distributed, so this one you should not look at the spatial. So it's locally, it could be anywhere along that curve, the heat junction curve. So I think that's a good place. I think back to the same point that I want to start where I want to stop. Next time. Not give a very good thought. That's where we stopped in the last lecture. It's about comparing the P junction, a diode, with a Schottky barrier. Schottky, you can think about on the left is a Schottky diode, on the right is a P junction. And when you look at the current voltage characteristics, it's very similar, right? Except that the coefficients are different. The saturation, this is usually called the saturation current, and saturation current for the this is a metal semiconductor junction, right? Schottky junction. And in the case of metal semiconductor, another Schottky barrier, the saturation current is relatively very high. And in the case of the P junction, the saturation current includes the band gap and includes the diffusivity of hole. So on the P side is really hole that carries the current. On the N side is the electron, so diffusivity of electron on the N side, diffusivity of hole on the P side. And then we have this one, the time, recombination time. This is say when you create an electron hole pair, you excite the electron from valence to conduction band. How long they can be kept separate, and after a certain amount of time, they will recombine and give off the either photon, as where laser or light emitting diode if you want, or give off heat, the generate photons. So this is the recombination time for hole and electron. You can see that the difference is really in this saturation current, and sometimes equal for dark current in mathematics. But I want to emphasize another fundamental difference. Yes?
Right. I would have thought sort of intuitively that the longer the recombination time, the more current you would have.
The longer the recombination time, yes. Let's say recombination is also related to longer recombination. Longer recombination, smaller dot current. But I see your point, where if the longer is recombination, essential recombination happens in this region. Okay, so I think that in that case, what happens is the diffusion supply is also limited your current flow. So this is where I want to emphasize the important difference between these two phenomena. Is the Schottky barrier. When electron go from here to here, right? It's electron. It's still electron. Right? The way I draw it. Here is the electron, and the metal side is the electron. No problem. Now, if you look at the P junction, okay, on the N type is electron, and then the P type is hole. So if electron go, so I'm drawing here, electron go from here to here, go through this space charge region, there's no more electron. Right? You get to P type region. So what happens? And you have to have current continuity, the charge has to be supplied, right? So what happens is that the hole will recombine with this electron. Okay? So the hole recombine with the electron, that means you have to supply holes from this side. So you draw a hole from this side, recombine with whatever electron comes this side, and this is where the recombination region happens. It's not in the space charge, it's slightly just outside the space charge. So it's a melodic carrier device. That's a really fundamental difference between majority carrier device and minority carrier device. Minority carrier device, this recombination is crucial. And later on, we'll talk about solar cell. That's all people are trying to refine solar silicon. It's trying to increase this recombination time. Okay? So so you brought this is the point. It's really important to appreciate the minority carrier device in junction. Okay? And of course I mentioned, so this is what I drew, the curve. You can see electron diffusion, Because on this side, so hole diffuse, when it comes to this side, there's no more electron, right? So electron will recombine with hole, so there's less electron flux forward. So there's small. So if I look at electron current, it decreases in this recombination region. And then I look at the hole current, right? Say on this side, the hole decreases in this region. That's where the supply recombines with electron. So electron goes through this space charge region. Let's neglect that in space charge they don't have recombination. So as an approximation. So it's a constant. And then after space charge, they recombine with hole. So electron diminish. Now at this side is just overflow. Right? So that's how we go transit from an electron to a hole. So the pin junction theory sharply the pin junction with the, I think say 3 people got the Nobel Prize. One is Shapley, and the other is Badin, and the third is Brayton. And I think it was Shapley and Brayton did the invention, and Badin was the manager at kind of built that. And he developed the theory. And then if you look at the history, and Badin, Badin is the only one of the guy got 2 Nobel Prize. Superconductivity also got Nobel Prize, right? So he was very. The history of the first invention. Badin as a manager felt this is so important. He has to do something. He developed theory, okay? But this is a very ingenious theory to think about how electron on this side moves, and hole on the other side moves. By the end, your current has to be continuous. The summation of electron current and the hole current is constant, right? Okay. And in the last lecture, I also said if you look at the energy flow, and when electron are here, yes.
I would like to know what happens in the hole current in the contact, because in the cables we must have electrons, right?
In the contact, so it's a matter of there's no hole. Again, there's no hole. So typically in contact, people want to make an omni contact. So what happens is when so the whole motion is really the majority of electron motion in the p-type region. So when hole move this way, go from hole move from here to here, that means this electron goes out to the metal. So that's what happens. Okay? And they have for the capital potential, electrochemical potential. That's what say at the junction. It's sort of like the Schottky barrier, but they want to make an ohmic junction at those sides. And if you think about the Peltier effect, right? Peltier heat is the kinetic energy part, which is 2 kg of the charge, average speaking, minus EC minus EF, right? The chemical energy. And then you look at this, EC and EF is growing. Here on the N side, EC minus EF is here. In the space charge region, it's growing larger. So electron is carrying more heat. Per charge is carrying more heat. Right? It's carrying heat out of the space charge region. That's why space charge region is actually a cooling. Okay? And then in outside, the immediate outside space charge region, recombination happens. Right? Recombination dump the heat just immediately outside the space charge region. It reflow back, of course, junction heats up. But physics is it's not the junction, the space charge region that really heats up. The heat is actually generated outside the space charge region. In this recombination, this is where heat is generated. That's a fact that most people probably don't know. Okay? So, to finish what I was talking last lecture, the rest of this is more the research. This is say the basic physics, and since we're talking about the Richardson formula, thermionic emission. So there are people doing, for example, in the this is the conduction fan. If you don't have a Fermi level around this place, the energy electron below the Fermi level is actually carry negative energy, and the electron above carry positive energy. So one idea is that if I do a Shockley barrier or potential barrier, right, and I just scatter this part of the electron, that's called energy filter, or depends on if you have interface, you also call it thermionic emission. So some people call this thermionic emission is, say, thermoelectrics, they have thermionic effect, or they so-called solid-state thermionics. But say, essentially, it's cutting out the low-energy electron, or sometimes it carry negative heat because the electron below the chemical potential carry. And if I draw the disk states, most time I mentioned before when we talk about thermoelectric, the disk states need the sharp feature. The sharp feature help increase the thermoelectric effect, right? So the way I view this, okay, in this region I cut it off by transport. I cut off transport electrons. I still have the electron, but they are scattered. They don't move. So then the real ones are here, and I can think this about that sharp region. So that's the way I say, okay, it's all really coming back to the idea. If you can create the sharp features in these substates, put a lot of electron there, and you can potentially improve the electron power factor, S per sigma. But see, the key is you only want to scatter this part, you don't want to affect this part. You do it. So that's still a lot of traits. I think that this idea is still not fully convincing yet to me. And I made a few slides on this. That's on my own sort of toy baby. I published a paper before. There's no experiment, and maybe some of you will be interested. But this is the issue I was addressing. What is the evaporation, right? I said that the the molecule coming out of the liquid surface, that's like an evaporation. That's equivalent to thermionic emission. But see, how about I have a vacuum here, right? I got a liquid here, and then suddenly a drop of liquid drop into the vacuum side, and every atom suddenly expand. Is that corresponding to evaporation? And I have a solid state case where I'm comparing these two examples. And these two examples is, one is a thermionic barrier, as everybody talked before. When electron flow this way, the low energy electron in this region is scattered. That's thermionic. The other case I consider, this was actually a paper Journal of Applied Physics, is what about I flow electron this way and suddenly drop a letter? And that means to me is more like I take a droplet and put it in vacuum and suddenly evaporate. And this one is more like I have a water surface and the water molecule coming out of the surface like cool water, right? So that's a solid state analogy that we're trying to make. So what I did is I did some energy balance analysis. This is essentially a Richardson formula type. And you can assume the two sides has different temperature even on the both sides, and different chemical potential. Okay, the real way to do this is solving Boltzmann equation. Very complicated. I don't know how to do it. So you solve this actually problem. Even when I tried to do the Fermi Dirac, it took a very, very detailed, very hard calculation. But when I just do Boltzmann statistics, you can do your derivation. No Boltzmann statistics, energy balance, current balance at the interface. And what I found is that this is the electron temperature on this side. The electron temperatures are 1 and 2, just right at the interface. It turns out that when I go down a step, there is an amplification factor. This is the potential high in kVt, and this is a mean free path. So normally this is very small because mean free path times temperature gradient, just a temperature drop using one mean free path. That's usually very small. But what I saw interesting is if I have this structure, I suddenly like the electron expand, actually raise this temperature or create a large temperature drop. That's an amplification factor. I can amplify how much electron temperature drop at the interface. So that's what I call potential amplified. On the other hand, my two base structure, same analysis, didn't have that amplification. So I followed up. I said this is the Boltzmann statistic. I did the Fermi-Dirac statistics, and as well as some equations. And this is the equation. This is the electron temperature at the interface. And you can say you can actually drive thermally just with a temperature gradient. You can drive electron and photon out of equilibrium. And this is the electron temperature jump at the interface. But if you do the reverse structure, there's no discontinuity at the interface. So this way, since it can help the efficiency of cooling, but so far I have not, like I said, this is just a theory, no experiments. Okay. Now I want to move on. That's just as an example. Sometimes it's interesting to twist and think whether you can have new ideas in this field. Now coming back, now we'll talk about the photovoltaic cells. And this is the PN junction I just showed, and the saturation current. Sometimes people call dark current. I don't need to detector dark current. And now we have a photon comes in, generate electron hole pairs. So if the photon energy is larger than the band gap, the band gap is always the same. Everywhere band gap is the same. So if the photon energy is larger than band gap, it lift the one electron from the valence band to the conduction band. Right? And this could happen anywhere in the device. That depends on where the photon is absorbed. We'll talk about that later. Right? So what I'm drawing, just okay, if my photon happen to be absorbed within the space charge region, then the electron hole pair is generated within the space charge region. Go for it. Right? Now, what happens after this generation? Of course, they have tendency to recombine. Right? And if you recombine, your photocell is a failure. You don't want them to recombine. You want to separate it. And now, if it's PN junction, if we in the space charge region, there's one advantage. Because electron, now there's an electric field inside. So electron wants to go lower energy this way. Hole is the higher energy is the hole, positive is the higher energy. Electron, let's say higher energy. The hole go this way, positive side. Okay? Just going down the potential hill. Now, this is the potential hill for hole. This is the potential hill for the electron. Going down there. That's natural tendency. And this natural tendency, so now you got more electron this side than, normally at equilibrium there's no voltage, right? Now you accumulate more electron on this side, you accumulate more hole, so you generate a voltage. Okay? And once you generate voltage, this voltage will drive your diode. Right? Just like on this side, if you have voltage difference, you'll have a diode current here. So now if I have light comes in, this is the current, the electron hole current generated due to absorption of photon. And now once I build the voltage, this is the current to the forward that balances it. Right? This is now when I have voltage, I drive the diode, and this is where I have a electron hole pair generation, the counter going this way. And of course in a solar cell, I want to go this way. I want this is less, than this. Okay? So that's the, if you understand that, that's the solar cell. Okay? And you can, so this one, if you, I want to call the short current, short circuit current. If the short circuit, the voltage difference is 0, right? You short it, this, there's no resistance, then this has to equal this, no voltage drop. That's short current, short circuit. Short circuit, volt when equal 0, that's your current. JL is your short circuit current. Right? Okay, now I'm going to, with that, starting from there, the rest is simple, just math. I can say what's my open circuit voltage, and my open circuit voltage is just to say there's 0 current. So if I set this side equal 0, I find out what's the open circuit voltage. That's the open circuit voltage, and you can further simplify because we know JS is set to dark current, right? Look at it. This is called dark current or saturation current. And I want a high open circuit voltage. What do? Smaller is better, right? JA smaller is better. You look at it. Smaller JAs, higher open circuit voltage, right? So JS power recombination time is longer, JA is smaller, right? So I don't want the recombination. I want the long lifetime for the electron. Basically, I want long lifetime so I can extract out. Okay? And you plug in the JSA related to all diffusivity, recombination time, and I'll write it down out here explicitly. You substitute in, if you approximately drop this one, that's what you get. That's just mathematics. We need to do on this. Now, of course, open circuit is useless because there's no power output. In real operation, we always have a load. We have current flowing. So when we have a current flowing, we call it power. And so, but before I do that, I want to show you if you draw this current voltage. So this is your short circuit voltage for 0. Short circuit current, negative. Right? When current is 0, open circuit voltage. Okay? So it's more like you're shifting diode parallel down. This, if you don't have a light illumination, it's a diode equation, right? That's a diode equation if you don't have this part. Just shift that diode curve down to the negative, the force pole branch. Okay? And of course, you can look at this. The power output is the voltage times current. So somewhere, your voltage times current, that's this squared. Depends on which one you're operating, you'll have maximum. And that's how you optimize. You change your load resistance, okay, so that you can control the current and the voltage by changing external load resistance. So that's a load measure. You do that for thermoelectrics, you do that for solar cells. Or so you need to optimize. So some people just design their circuit to optimize. And very often people don't draw this way, just reverse it. That's just for convenience. So that would be another way to draw, but that's the real one is actually to be on the electric side. Okay? Now we can go to the maximum power. When the power output is maximized, this is the current times voltage. That's the power, right? So you just take the derivative of your voltage and say when it's maximized. When you take derivative, physically what you do is I'm changing my external load to find out where is the optimal voltage, so that the power is maximized. So that if you take this derivative, you'll find out where is the optimal current, where is the optimal voltage. Okay. And again, see, this is just mathematical detail, not important. But very often in the terminology, people say, "What's your fill factor?" What is that? So this is the rectangular. This is where you optimize. You run your optimum current voltage point, right? So that's the actual maximum power you have. And if you look at, if you draw another rectangle, where you draw this set short circuit current and open circuit voltage, you draw another rectangle, right? This ratio of this actual power divided by the outer rectangle, that's your fill factor. And you want to fill as much as you can say, to get the maximum power. Okay? Now let's go to source term. Source, this is a electron hole generation, right? So I have the radiation coming in. Only electrons, photons with energy larger than band gap can generate electron hole pairs. So, and also, let's suppose this is a black body. Let's treat the sun as a black body. Okay? So the solar radiation comes from the sun, and this is the fraction of solar radiation actually, so you have to look at the distance, the fraction of solar radiation, because the black body of the sun is 5,800 Kelvin. You know it's not just a closed object, 5,800 Kelvin of cool, right? It's very far, it's diluted. So that's this fraction in radiation called effect. But it's not the radiation intensity, right? It's the number of photons. Because each photon generates one pair of electron hole. So I'm looking at the energy, because this is the energy. That's the energy of per photon. So I divide that, that's the flux of photons coming. It's not the flux of energy. It's the flux of photons coming for the solar cell. And this is the reflectivity. I assume that the radiation getting into the cell is absorbed the general electron pair. That's of course an idealization. You've got different losses. This is just the best case. And of course the maximum best is no reflection. So that's 1. Okay? So this is the source term. And the good thing is the source term depends on only the temperature. If you idealize, depends only on the temperature of the source, right? And when I calculate efficiency, this is the energy of the photon coming towards the cell, and this is the power. So of course I want to maximize the efficiency. Everybody wants to maximize. And then the question is, what's the maximum? How much you can get, right? Second law. First, the solar cell is limited by second law column. You can always say very safe. The maximum efficiency you can get is the heat engine between sun and the earth. So Tc is 300 Kelvin. T hot is the 5,800. So that's calorie efficiency. That's an upper limit. After the upper limit, you can't get anything beyond that. Yes.
I'm just curious what the way that the picture you have on that slide. So it's actually instantly on the p-type, and then don't we want it to hit the say charge region ideally?
Okay. So the photon could be absorbed along the even absorbed here.
So some of them penetrate, right?
Yeah.
Okay.
So if photon absorb here, how in space charge region? They have less probability to go to the other side, the electron. They diffuse, you'll still diffuse. There's some diffusion happening. Just to take a more, say, the chance of getting there is less.
So that's why we want it that way and not like you see how that is the PN region, like the TA when you drove. So
you want to have a longer potential field. Drive the actual use the field, right?
I'm talking about like there's a picture right there. They're being thin and flat PN.
Really thin PN, of course, the good thing is your electrode is very close. You can get to the two electrodes, but your photon may not get absorbed. So this is another thing that we're going to talk. That's your battle. Your solar cell is always your battle. One, you want to get photon absorbed. Two, you want to get the charge to the electrode before they recombine. One wants center, the other wants deeper. This is essentially the thing people are trying to solve. Okay? But the question we want to ask is, what's the maximum pulses? Okay? What's the maximum possible emissions? And this one, anybody's do solar cell, the first paper you read, you should read, is this paper by Shockley. It's Shockley-Pfizer limit. Okay? That's what Shockley-Pfizer limit we'll discuss next. And of course, the real dial, right? The real dial is hard to get to what's maximum because the saturation current depends on the field material, recombination time, diffusivity, electron volt. It's hard to get your maximum. And the ingenuity of Shockley, I read a few papers, very, say, smart guy, and he's a physicist. So this is what Shockley can. So if you think about PN junction, put it on the side, right? Open circuit. Of course, the solar radiation will create the electron holes continuously. Every photon will generate electron hole pair. If there's no recombination, no defects recombine, what happens? You got to have the natural recombination process, right? Spontaneous recombination. Give out photon. So that's your maximum limit. No other recombination, only spontaneous recombination. But what's that the spontaneous recombination rate? Calculate that out. Okay? And I'm really impressed. I read a few papers. This is where every time I do this, I have a place where I don't feel comfortable to tell you. And I want to tell you because I want to go to find out. And this is not just that I read it yesterday. For many years, I tried to understand this. I still don't fully appreciate, feel fully confident. This is this expression where it came up. And this is actually not in Shockley's paper. This is you can check Henry's paper, and Henry had another paper by Ross, and they all discussed three different Shockley's paper, Henry's paper, Ross' paper, three different ways to write this expression. And so when a PN junction has a voltage here, and what's so we say the quantum state, the Fermi-Dirac Bose-Einstein statistics, right? But what they derive the photons, which obey Bose-Einstein statistics, in the PN junction, everything looks like Bose-Einstein except that we add an E wave. Okay? E wave is if you look at E wave is really the terminal over here in the N type, terminal in P type, in this region. That's the voltage, E wave. It's adding this term that I just feel I can't comfortably derive it. You can go to expand, so each paper you start from different place. And I will encourage you to read. And again, if you have any idea to make myself comfortable, I will come to my office to discuss. Because I for many years, we're actually looking into this, see how we can really make comfortable or derive some near field, under near field where it's value or not. But see, so I can only just say, take it from here, I can explain it easier. And the recombination, go to recombination, PN junction, and particularly this is if you do lasers or light emitting diode. This is a very often people stop, okay? But I haven't seen the one that really explained to me from thermodynamics very easily. So that's the per mole, quantum mechanically, per mole, how many photons you have at the equilibrium. Okay. Now starting from here, you can derive what due to this recombination. Now you have a voltage, the arbitrary voltage. What's the recombination part? So you just integrate again from the band gap to any energy. And if you do Boltzmann statistics, you just neglect one factor one. And this is the I'm later I didn't write the equation, but it's copied from Henry's paper. And this is solid angular integration. So that's essentially the photon density of states inside the crystal. Photon density of states. So it's a Fermi derived, quasi-Einstein statistics integrated quantum density of states. So this is the spontaneous emission due to the current that can create at arbitrary voltage. Okay. And everything is very similar to what we had before, except that A is a lot longer. That due to, if you look at the diode A, right? This is the A for the diode. That's determined by axial material recombination. And then here, the ingenuity is, no, this is really just a dielectric constant refractive index. Band gap on the material. So this is the maximum you can have. The best you can have. Now as a really new recombination. No other defects in recombination. So because of that, it's free of any material. So now you can derive the maximum. But it's still one material, that's the EG, right? This is the only other material you can have. But when I talk, you can also say, how about the photonic crystal inside the photonic crystal? This factor we checked. This is spontaneous solve. And maybe you got a different maximum. Maybe a good people. Okay. So now I have translated if you look at the term, this is the current term, the diode equation, right? One is the diode equal current. The other is the photon generated current. So this is the photon generated current. In the best case, this is the one. So I put in the best scenario, and everything is the independent material except the band gap, only the band gap. So that's where Shockley to derive what's the maximum. And this is the curve was not copied from Shockley, but from Henry's paper. And using this rigid recombination current, photons generated electron hole pair, so this is the photon generated current, and you do the rest of the analysis just as we did before. You can find out what's the maximum power and what's the maximum efficiency. And this is what Henry calculated. And here, C is a concentration. What concentration after concentration? So what it does is change JFL, right? If you concentrate more, you generate more electron hole pair per unit volume. So this is if you concentrate, you get this larger, you get a larger open circuit voltage. So concentration actually can help you increase efficiency. Okay. So not too much increase, but reasonable increase. And what's interesting, you look at it under 1 cent condition, right? Where is the optimum band gap? About 1.5. Now you look at the material. Where is about what's that material? 1.5. Gallium arsenide is actually very good, right at that target. Silicon is here. 1.1. Not too far from the optimum. So this is about 31%. Okay. So that tells you if you build a silicon cell, this is about the best you can do in terms of efficiency. And of course, without yes.
When you look at just the normalization of the energetic photons compared to the band gap,
You mean
you have a certain energy.
Right.
What happens, for example, for glucose? They are high energetic.
Right.
They are absorbed and in equal energy as the 1064, the 1100. So the thermalization is the energy.
Right. Exactly. So this is a black body curve, right? This is your band gap somewhere here, okay? And really, what's useful energy, because this above the gap energy is lost. So if I look at this is the band structure. If I have photon generate electron hole pair this way, this energy electron relax bottom very fast. Okay? Hole relax to here very fast. So this is the heat. And in fact, people have been theorizing hot electron cells. If you can extract this electron out with this kind of energy, that's hot electron cells. Question how you get it out before it relax. This is about picosecond. So picosecond is very fast. If you times 10 to the minus 12 times diffusivity, just travel nanometers or few nanometers, just have no way to get it out. Right? But so if you have good ideas, that's something people been thinking for since 70s. Okay. So that's a single junction, maximum you can get. And exactly on this issue, right? How about we do multi-junction? Right? One cell, so multi-junction, like shown here, the first one absorbs blue, so larger band gap, the topmost layer. And the longer wavelengths, lower energy can transmit through. So get absorbed the second layer and get also third. That's the idea. And of course you can see with this stacking, each one generates a current, right? If you look at this, the key is that your current has to be continuous because you put an electrode on top, the electrode on bottom. So each cell has to generate the same amount of current. That's a design nightmare, almost. Right? And but people have done that. It's a material nightmare and a design nightmare. Okay? Design in the sense you have to get a current match, so the electron come from the top layer has to go to the hole of the next layer, or hole of the top layer has to merge with the electron of the next layer. Right? The current is continuous. And you have to group different materials because recombination is a killer, right? So that's why people do molecular beam match, lattice match. They generate defects, they generate dislocations. These were just the centers for the recombination. And then you kill the electrons before you can take it out. So to grow those material, people done molecular beam lattice like a spectral diode lab. And they were doing laser before, now they're doing probably 41% for cells, triple junction cells, 3 junctions. And that grew lattice match this one. And so this is, I got one graph from the internet. I think it gives some idea. Silicon in real world deploy about 15% to 18% large scale. And then gallium arsenide 30%. And now this is a triple junction, indium gallium phosphide, gallium arsenide, germanium, you look at band gap 1.8, 1.4, 0.7, or other material. You have to look at what are the materials that match your current, and then you can grow. So you have to look at both material and band gap device. And if you do really well, how much you can do, right? Infinite. So this is a previous paper. They showed 72% that if you got 36 back, let's say multi-spectral, each 36 stage. Okay? And if you have an infinite stage, the theory is about 86%. That's the best you can do. Around 86%. Infinite multi-junction. It's still lower than the color between 300 and 5800. That's about the line. If you do 1 minus 300 divided by 50, 100. Okay. So that's what people can do. So in theory says, now you look at the practice. In the lab, this is the best in the lab. It's not best deployed. Silicon, where is the crystalline silicon? Crystalline silicon, yeah, here. This is silicon. That's a function of year, right? The best is about 25, 26%. I remember I once went to Martin Green. This is the University of New South Wales. Martin Green is probably the biggest guy in the solar cell. I went to his lab, and they told me about 27 here. That's the remember. Shockley Pfizer gives you 31%. So they are doing really well compared to that limit. Amazing. And also, so that's why so all your potential is also limited. That's the best you can do, right? But in fact, if you can really do that at low cost, I think your problem is solved. Here, you can always work in lab and make better one, but if you can do that at large scale, the problem is the engine is only 10%. Also, of course, power plant is about 40%. And so the best multi-junction cell, right? SPEP lab. Here is less than, but I think that now the best I heard is about 41%. Okay. And this is a multi-crystalline. This is a single crystalline, multi-crystalline. And let's look at amorphous silicon. Amorphous silicon here. Okay. It's well, the real world is about 6 to 8% deployed. The best in the lab is about 12%, but that's a fewer junction, not just a amorphous silicon. And this is a say copper indium. The 6 copper indium dicyanide, and so the best is about 19%. And telluride is a dark quartz here. And because, as I said, it's dark quartz because most people talk about 6 before, and now First Solar is probably the best, most profitable company in the telluride. And their sale, I think, is around 20%. It's a from lab to real production, there is a difference. And then this one is the polymer, I think. Okay, organic cells. And then there's a dye cell, so-called grasses cell. That's about 11%. So this will give you working power. Not the most up-to-date in years, but pretty close. What are the problems? Right? I mentioned the one for solar cell, the number one is a larger device. That's the Akimi cell. A large device, very sensitive to recombination. So, what are the creation? What are the reasons for recombination? Those impurities. Particular impurity in the bank, visit deep in the bank deep level. Those are recombinations. Dangling bonds, attract charge, right? And green boundaries, where you got a lot of dangling bonds. So those are the regions where the recombination happens. And that's why people purify silicon, crystalline silicon, give an example. Very large grade is about $2 per kilogram silicon. If you want to make a solar cell, you get you re-crystallize it, purify it, and got to $40 per kilogram. And then, of course, during the process, you use a lot of water. Like you heat out, melt it, and re-crystallize it. And in fact, last year, before the market crashed, everybody was on silicon, so the silicon was short, and that got to $140 per kilogram. Okay, so that's let's say minority device Achilles heel. And in that sense, I can argue thermoelectrics is good because it's a majority carrier device, doesn't have severe recombination problem. And the other problem is this absorption. Okay? In fact, this is, to me, I say, okay, photon comes in first step, absorb. The second step is the charge where it goes. So this is really the first step. And look at where the photon goes, right? Of course, in the interface is reflection. You don't want the reflection. You minimize that. Reverse coating, surface treatment. But once you get into the material, you don't have almost no other ways to control this profile anymore. It's material intrinsic absorption. So this is the absorption coefficient, and decays, the intensity decays exponentially. So now you think about in your most photon generated electron hole pair, let's say in this region, and you want your space charge in this region to overlap it, so that you can separate that. You can use your field to drive electron to one side, the hole to the other side, right? So the depth of this 1 over alpha gives you exponential -1, so that's called the calculation depth. So this is where you look at the material, what I should choose. Okay, absorption coefficient. Absorption happens above the band gap. So band gap is the first step. And then you look at the material, you say, oh, silicon, we know so much. That's the hero of silicon. Why silicon is a problem? Because it's really just, first thing is because this absorption. You see here, absorption, this is the photon energy, right? Band gap is about 1.1 electron volts. It's a very slow curve. And if 1 over alpha, so this is centimeter, so here is about 10 micron. So if I use a 10 micron, so the energy below 1.6 eV, those part of the energy is absorbed very little. It goes through the cell. Right? It don't get absorbed. So if it's too thin, this part will go out. So that's the absorption. And that's why someone say like copper indium like sigma 6 pattern turnaround. Right? They have very sharp 10 to the 5 fixed power. So if you have 1 micron, this is the inverse is 1 micron. 10 to the 4th inverse gives you 1 micron. This is centimeter. Okay. So with if you want to use thin film, direct gap is a good one. Those are good with thin film. And that's why when people make amorphous silicon thin film, it's pretty good here. This is useless here. Right? You can generate electron hole pair, but you don't have much time. So solar cell is always incidental. First you want to absorb it. Second you want to get a charge to the electrode. Right? So why is silicon so different from the others? Gallium arsenide shoot out directly. Right? This is what I mentioned before, whether it's a direct semiconductor gap or indirect gap. Gallium arsenide, all the others that have a sharp increase, it's direct gap. So the photon go from here to here. If the electron from valence to conduction band, you need to satisfy the energy conservation. So the photon energy gives the difference of electron hole energy. So that's the energy conservation. And second is the momentum conservation. So you have to, momentum is h over lambda, right? Lambda of photon is a micron. Well, lambda of electron is lattice constant, Armstrong. So in this is a 1 over Armstrong, but so 1 over lambda is essentially vertical, so the photon don't give you much momentum. That's the problem. In indirect gap semiconductor, right, the band gap is here. When you want to say the momentum doesn't match between electron and hole. So if you want to leave this electron here, the photon don't have enough momentum. It has energy, it doesn't have momentum. It has to have something else. That's photon. You can emit a photon or absorb a photon. Photon doesn't have much energy, but it has momentum. So this is why they say, so you got to have either emission or absorption of photons. So you got to have 3 people now. Like I said, very hard to schedule 3 people together. So the absorption is weaker. Because when the photon wants to do it, there's no photon there. Okay? So that's the dilemma why the silicon don't have good absorption there and near the back gap. And of course, once you move to this region, it goes up. You can go just from here to here. Right? Okay, so that's what I say. Solar cell essentially, you solve one problem, maybe the other problem. Thick or thin, and how you can address those issues. This is the really electron thin is better. You just take it out before they recombine. You send to the electrode. Photons you don't get absorbed. Okay. Of course, that's related to efficiency, and the thicker thin is directly related to how much material you use. That's a cost issue also, right? To have a low cost, you need a thinner, less material, so always the material cost is better. And you look at the cost. Now the lowest solar cell is from First Solar. They say they have manufacturing cost is about $1 per watt. Okay, and this is where the grid parity is from the factor of 3, assuming a certain amount of year you use it in your work. Factor of 3 less, you have $1 per watt. And it's good. It's a good curve here in terms of the cost. But say, look at the get terawatt. It takes a long time. Right now, the worldwide installation per year is about 6-7 gigawatt. 6-7 gigawatt. China put a 100 gigawatt steam turbine every year. Okay, so it's just a block, really just a block. When you say about doing a Walmart park, we need clean energy. It will take a lot of effort, really big. Okay, different type of solar cells, right? And silicon cell is most predominant. Color is the cost, right? Single crystal, multi-crystal, colorful, as you can see the greens almost, right? And what's interesting is all those crystal surfaces have texture. And that's to trap the light so that to reduce reflection. Reduce reflection, not only reduce reflection, once you get into the backside, if it's a metal, you reflect back, you don't want to go out some of the photons, so the more light you trap. And the difference between single crystal or multi-crystal is single crystal, you can get a regular texture, multi-crystal is not get a regular texture. Just a manufacturing process and crystal etching. Right? And then you got say electrode and silicon here. You can say this question here, if you generate electron hole pair here, it has to diffuse. You can go both ways. Right? You don't have a field. You have to design so that the field can help you go one direction.
Because why P-type is much thicker than the N-type?
No, it must be related to the material characteristics. I would imagine probably P-type has a recombination better. I didn't check. But most times people use P-type something.
Even beyond silicon? Even beyond silicon, if the material is not silicon?
No, material not silicon, then no. That I don't know, I didn't check. Did you check? Okay. Right. And you can see here, P plus, try to make an ohmic contact. Right? Reduce that Shapley barrier. And you have a top electrode, metal grade. That's a Shelby effect. Metal grade, the photon don't get through. That's not good. So sometimes the people even bury the grade down or make it on the backside through vias. So there are a lot of nitty-gritties improvement, a little bit of improvement we put down over the years. Thin film. And here, say, most early one is the monosilicon crystal. A monosilicon, we showed before, absorption is pretty good, so you can use thin. But the electron, amorphous material, electron is very hard to move. A lot of damping bond recombination. So you got to use really thin. The amorphous silicon cell is about 200 nanometer. And if you can reduce that to even thinner, it's probably better. Too thin you manufacture is a problem. Your pinholes, all those, they're always filled up. Okay. But this is actually showing you just a multi-junction. Say if you look at it, this is on scale, and top is a transparent electrode. So unlike silicon, you look at the electrode on the top, right? It's spaced apart. So electron go here actually diffuse to the electrode, laterally going to the electrode, right? Silicon is reasonably good in terms of recombination. Amorphous silicon don't work. So you got to have the electrode right on top of it, right? So it's a transparent conductor, And this is the cathode, right? The active region, about 6 microns. And this is 6 space, active region 1 to 3 microns. It's a trade-off between recombination and absorption. If you increase absorption using thin, it's always better. If you can, theoretically it will be better. If you can use thin, the first step you can trap the light. That's why we're doing some research in light trapping. If you can trap the light, it's always better. Use it thinner. Help the electron.
The thickness of IQ is what? I can see the number.
ITO here is about 0.5 microns. I'm not sure whether that's the best. People are optimizing. I'm just a copy from where I was trying to show the scale relative. So people are doing transparent conductor also trying to improve the conductivity. Basically, you want a very highly conductive. So if you're highly conductive, the thinner is better because the free electron in this material also absorb photon, which generally you don't want that. Polymer cell, right? Polymer, ideally, if you put polymer, you reduce the cost, ideal situation. The problem with the polymer is that it's even worse than amorphous silicon, right? You generate, they immediately recombine. Recombination is very fast. In fact, when you first generate, they bond it together. They are not even separate the electron or hole. This bonded state is called an exciton. So MIT has an exciton center, DOE center, Macrodo. We have I have I'm needing a solar thermal center, Macrodo is needing an exciton center. And there is the whole issue is to find how I can separate this exciton and make the electron go one way and the hole go the other way. It's also right. So in that case, you look at this really thin, 220 nanometer, trying to separate. But that's still difficult. So people are now doing the so-called bulk junction cells. So you put a two type of molecule, one conducting electron, one conducting hole. So locally you generate electron hole pair, and idea you want to immediately separate. So the electron go one molecule, then go to another molecule. Graxel cell, right? So this is not a solid cell, it's actually a liquid cell. And what it has is titanium dioxide nanoparticles. Okay? titanium dioxide nanoparticle has a bank of about 3 electron volts. Too large, not much more photon there, right? And so what a brass cell does is you put a dye on top of that titanium dioxide, and this dye is called a photosynthesizer. So this is where photons absorb. And photons absorb dye molecule monolayer, okay, generate electron hole pair, exciton. Before they dissociate, they are exciton. And you want them to dissociate, separate into electron and hole. And the electron go immediately flow into nanoparticle. So the nanoparticle is diffused. Now there's no field. Really diffusion process. Okay? So they zig around out. So that's why people try to do nanowires so that give a better path to electron rather than nanoparticle. But the problem is that when you do nanowire, your surface area for absorption also changes. Right? Here you can have this area, surface area, volumetric. Your nanowire is only this surface, right? Vertical. So the surface area of absorption. So the particle has advantages just almost like a 3D wrapper around the particle. There's more particles. But there's always this everything to trade off. Right? And what about the hole? Turns out the hole goes to the liquid. And this is a chemical reaction now. It's not just a hole diffuse. In liquid, there's no hole cannot diffuse. So the hole oxidizes the molecules. In the case of very often it's an iodine. Iodine in the liquid get say iodine 3, and this charged molecule diffuse to the counter level. So again, diffusion. So electron diffuse to one electrode, hole diffuse to the other electrode where they are reduced, and the reduced diffuse back. Sounds like a very cool process, right? The idea is again this you can compound. But see, Russell was pretty good in getting the 11% out of this. And so this is a flat surface versus nanocrystal electrode outside absorption. So that's pretty much what I want to say, and then we're right on time. And this is the sort of dream. Okay. The dream in the sense, here is the cost, here is the efficiency. You want the low cost, high efficiency. Right? Silicon is typically in the first generation called Gen 1. Thin film is here, lower efficiency, but lower cost. And in fact, they made a good business, at least for first solar telluride based. And people are thinking of very soon go to Gen 3. No winner in Gen 3 yet, okay? This is where you guys